Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to calculate evapotranspiration for Landsat images in the Earth Engine platform. You can use my YouTube channel, Google Earth Engine with Emerson Ahrari, to learn more about the Earth Engine application in Earth Sciences. So, if you want to learn how to do this in the Earth engine, how to calculate the ET from scratch, let's follow this tutorial. First of all, make a new Colab notebook. So, now here you can see the code editor environment, but I'm gonna show you how to do this calculation using Python environment in the Google Colab. So in the Colab environment, let's make a notebook in the first step. So before we start processing, we need to import essential libraries necessary to deal with the Earth engine in the Python environment. Let's start with EE and GEE map. In addition, we need to import xarray as XR. The X array is going to use for the multidimensional array structure, and I will show you how it can help us in this tutorial. The next library is the XEE library. The XEE is one of the newest library recently developed by the Google community that allowing us to actually combine the Earth engine and X-array structure. So let's run the first cell, and now we are importing essential libraries to start dealing with the Earth engine in the Python environment. If you faced with any challenge in this tutorial, you can go to my YouTube channel, and below this video on my channel in the description box you can find the example link, a code link that help you to find the errors or problems if you face in the code. So as you can see, now the first cell actually successfully ran, and we can clear the output. Let's make a new code. Now we need to establish a connection between Earth Engine and Colab environment using EE library. Start with authentication and initialize the account information. First argument is the project ID. Every one of you has a project ID in the Google Earth Engine. If you go to the code editor environment, upper right, here you can see your account information. Go to the project info and find your cloud project ID. Copy and paste into the code, just like this. The next argument is OPT URL. So search about the XEE on the browser, and then you will find a GitHub page about the Earth Engine and XEE. This GitHub page actually including a detailed instruction about XEE library, how to use it, and also different instruction, relevant instruction about the XEE. The OPT URL address, if you scroll down a bit, here is available, and just you need to select, copy, and paste to your code. Let's run. After a few moments, Colab asking you permission to get access to your Earth Engine account. Just click on Allow, and then you can select the Earth Engine account. Click on Continue and continue. So now the connection established, meaning that we can use the Earth Engine capabilities, functions, and data catalog from now on. So make a new cell, and now we need to select the region of interest. To do this, create a new variable like map. From GEE map, let's call the map function with a base map with a satellite view. So, and then let's run a map. In this tutorial, I'm gonna show you how to make a model for the evapotranspiration. So the base of tutorial is actually in this tutorial I'm gonna show you how to make a evapotranspiration model based on OpenET product. This is one of the newest ready-to-use ET products available also in the Earth engine that here offers evapotranspiration based on different models with monthly frequency and also based on Landsat resolution. For example, the ensemble monthly is a assimilation of actually assimilating different models into a same product. So, as you can see, this product is available since 1999 to 2024 with monthly frequency and 30-meter resolution. That is very interesting things. But the problem is this data set is only available for the United States. So, and at least now when I'm making this tutorial, this product is not available for all around the world, at least in the Earth engine. So now I'm gonna show you how you can make a model based on this product in the United States and how you can expand your model to the rest of the areas. For example, I'm gonna calculate the evapotranspiration for southwest of Iran, but this product is not available in this region, but it is available in the US. So now I'm gonna make a model in the US and apply it in the Iran to calculate the evapotranspiration for my own region of interest. Yeah, actually, I'm gonna show you how to do prediction, ET prediction, using Landsat images. So, and as you know, the evapotranspiration is a main factor in the agricultural area and also vegetated area. That's why I prefer to select an agricultural region to actually do the prediction and developing the model. In the northwest of the United States, here you can easily find the Idaho croplands area. That here you can see them distributed here with different shapes. For example, I'm gonna select just a small part of this area. It's important for me the study area covered by the agricultural region, covered by the vegetation, and showing the vegetation dynamic during the growing season. So now in the next step, I need to have this rectangle as a variable. ROI sets to from the map, select the last feature that is drawn. Convert it into the geometry. Let's run the ROI. As you can see, now the ROI is available actually as a rectangle with 5 vertices. Here you can see the polygon structure and relevant coordinates. In the next step, we need to call the OpenET product for example, a target year. In Iran, I'm supposed to predict the evapotranspiration or ET product for 2024, and now I prefer to select only 1 year for the prediction and training the model. So now a new variable like ET created. Make a tuple. Inside the tuple, here we need to call the OpenET for the US case first. So then define a filter date actually, and also we need to call the OpenET for a period of time for the sake of the modeling. So let's call a time start and time end as a separate variable explaining the starting and ending time. Time start, time end, just like that. 2024, 2025, filter date, time start, and time end, just like that. Then make a filter bounds for the region of interest or the ROI. I need to call all OpenET products for the selected area belongs to 2024. So as you can see here, we're supposed to have 24 actually ET product for this area because maybe my region of study actually covered by 2 different frames. So in this case, there is no problem. Then actually we can actually convert it into the monthly format with 1 image per month using a mosaicing purpose, and there is no challenge in this regard. But as you can see here, for each date we have 6 products, 6 bands relevant to the evapotranspiration, but the target band is ensembled band that is a combination of the different models, different ET models. So in the next step, I need to find some predictors for the ET that is statistically relevant to the evapotranspiration. And among the environmental parameters, vegetation cover and the temperature maybe are the main ones. So now I'm gonna actually create the monthly evapotranspiration. Monthly, I'm gonna actually call a monthly predictors like NDVI and LSD using Landsat 8 and 9 images for 2024 as predictors, because Landsat 8 and 9 and NDVI and the temperature dataset are available in all around the world. And as long as I have NDVI and temperature, I can predict the evapotranspiration for everywhere in the world, so there is no limitation. Although the OpenET is only available in the US, but the vegetation and NDVI, I mean, and the temperature is available for the rest of the world, then we can expand our model based on this relationship to the everywhere. So now another variable, Landsat 8, should be created. Landsat 8, we need to have the Landsat 8 and Landsat 9 together, because these two satellites is going to actually constitute our predictors. So Landsat 8 images, if you search on the net about Google Earth Engine and Landsat 8, you can easily find the collection 2 level 2 product. This product is atmospherically and radiometrically corrected, and it's a robust actually option for the data analysis because it's completely corrected and no extra analysis or at least the pre-processing needed. So Earth Engine snippet available here. You can call the dataset using a snippet tool and then define a same filter date and filter bound. So we need to make a monthly NDVI and temperature same as ET for the same period of time and for the same area, because first we want to make a model and it is important to have correspond NDVI and temperature for the evapotranspiration data. So dot filter bounds for the ROI. So let's ignore the Landsat 9 for now, and then we need to actually exclude the cloud from the Landsat 8 images and calculate the NDVI and LSD data. So now make a new function to manage all of these steps. DEF refers to the actually uses to start a function. The function name here is the OLI. The OLI is the sensor names in the Landsat 8. Each input to the function considered as an IMG. So in the first step, we need to manage the cloud cover. If you scroll down a bit here, you can find the QA pixel band with the bit mask information to actually detect the cloud cover in the image. So first of all, create a new variable selecting the QA band, QA pixel, just like this. QA pixel selected, and the next step is we need to use the bitwise structure to select the pixels included, the dilated cloud, cirrus, and also the cloud and cloud shadow, and etc. So here from the QA band and bitwise structure, it is easily to do this. For example, dilated band, here you can see sets to from QA band use a bitwise and a structure. From one, actually I'm going to shifting to the left by 1 bit. Bit number 1 showing actually dilated cloud, so that's why 1 shifting by 1 bit to the left. And then pixels not equal to the 0 selected. So this is for dilated. And then the cirrus band, the cirrus cloud, again from bitwise structure, bitwise and from bitwise and so bit number 2 from 1, actually 1 shifting to the left by 2 bits, and then select pixels not equal to the 0. The next one is the cloud pixel. Bit number 3 refers to the cloud. So here CLOQA bitwise and from 1 shifting to the left, or 1 shifting to the left by 3 bits, not equal to the 0. So, and then the shadow bit number 4, shadow QA dot bitwise and 1 shifting to the left by 4 bits. Select pixels not equal to the 0. Okay, all the cloud relevant pixels selected by a bitwise structure. So we need to make a mask or integrate or bring them all into a same variable as a mask. So deal dot and sorry, it should be or. It was my mistake. So dot or again, dot or cloud dot or shadow. So just like this. Okay, the cloud mask created. In the next step, we need to calculate the NDVI and surface temperature. We need to extract these parameters. So to calculate the NDVI, first of all, we need to apply the scale and factor on multispectral bands. From input image, select all the bands starting with BR and multiply them to the scale value, multiply to the scale, and add to the offset. Here you can find the scale and offset values. Paste into the code, minus 0.2, minus 0.2. This is the surface reflectance data. NDVI sets to, select the surface reflectance, then normalized difference. The normalized difference calculate normalization relationship between band number 5 as a near infrared and band number 4 as the red band. So, and the output name will be the NDVI. So the next should be the surface temperature band. Surface temperature is already calculated, just we need to apply a scale and factor here. So the temperature sets to, from IMG, select the surface temperature band, band number 10, ST band 10, and multiply to the scale value that add to the offset value. The output unit is based on Kelvin, or you can convert it to the, for example, degrees Celsius, but not necessary here because we don't want to make temperature interpretation or something like that. Only we want to make a model based on temperature and NDVI relationship with evapotranspiration. Finally, the function return NDVI with temperature together as a single data set for every date, and cloud bands or cloudy pixels already masked by the update mask process. So remember that we every data set here has a properties or metadata information, and system time start is essential, and we need to have it for the output. That copy properties from input properties, keep the system time start, because Our analysis is based on the time series and data acquisition already stored in the system time start property. So we need to keep it for the next step analysis. So then make a map structure. So we need to define a loop structure using the map. Here the map giving us a loop structure, and we are applying ORI function on the map in the loop area. So let's run the L8, but sounds something wrong. So bitwise and W is missing here. There is a typo. Let's run a cell again. Maybe still the same problem. Bitwise and so yes, now here bitwise and problem is fixed, and now you can see 42 elements returned, and in every element we have NDVI and LSD. Let's rename the temperature to the LSD, and now you can see for every date two bands available. One of them is NDVI, the other one LSD, and also we have a system time start referring to the data acquisition for each date. Okay, the data NDVI and temperature are ready for 2024 from Landsat 8. So we need to do the same process or follow the same process this time for the Landsat 9 images. So that's why another variable L9 created. L9 sets to make a tuple. This time we need to import the Landsat 9 image snippet, just like this. Let's copy and paste into the code. Everything is same between Landsat 8 and 9. Just use the same structure, use the same filter bound, filter date, and also the NDVI or temperature analysis. So you can see Landsat 8 and 9, both of them are ready, and now we need to combine them into a single data set. So a new variable Landsat created, get the Landsat, merge it to the Landsat 8, merge it into the Landsat 9. Remember to sort them based on data acquisition. Sort based on system time start. So let's call the Landsat again, and here you can see 86 elements returned. In every date we have one NDVI and LSD, and all of them, some of them belongs to Landsat 8 and some of them belongs to the Landsat 9. And it's not different. Both of these sensors and satellites are same. So by this combination, we increased the existing number of the number of images that help us to produce more accurate maps at the end. So Landsat data are available. Now we need to convert them into the monthly frequency. We already set the time start and time end. We can easily calculate the time difference from time end to time start. Time start based on months unit of measurement. We need to know how many months do we have between time end and time start. Remember to round it so to avoid any float value. So the time difference will be 12 because we only have 1 year and there are 12 months during a year. So the next step, we need to make a list of dates from early 24 to the late of 24. So here we need to a list of dates, ee.list.sequence, starting from 0, ee.number to time difference, a list starting from 0 to the number associated to the time difference. Remember to subtract from 1, it's already started from 0, And now we need to add the date to the list. So make a loop structure and define a function by lambda. Each actually mount interval called as x, and we go from time start to forward by x interval and mount unit. So let's print the time list and see how it looks like now. The time list is a list with 12 elements, each row showing the date of each month, as you can see, starting from January to the December 2024. Okay, now in the next step, I can make a function to filter the data sets like ET and Landsat based on each month date and calculate the average of each month separately. It is really easy to do. So another function as monthly created. The monthly function including two inputs. First is the date that's already available in the time list, and the second one is the image collection. So now start date for each month calculated from input date that is already defined in the time list, and end date sets to from start date go advance by 1 month. So the collection average sets to get the call image, define a filter based on start and end date. The function return the average image. Sorry, I forgot to get the average or median. The median is better for the NDVI and temperature in the Landsat images because less affected by the cloud cover or no data values. Finally, the median image for each month returned with a new system time start that comes from start date with millisecond format. So the function is created, just we need to apply the function on existing dataset. So let's start for the ET. The ET product actually for all area covered by 2 frames, and the monthly format help us to get an average for each month. Finally returns 12 image, 1 image per month for 2024. The monthly ET sets to make a tuple, bring everything into the image collection first, then get the time list from the time list. In the time list or in the existing times or the calendar, make a loop structure. Each input into the in this structure consider it as a x, and monthly function applied on each date or each x for ET product. So let's print the monthly ET now. Monthly ET. As you can see, now we have 12 ET products, 1 ET image per date. So it works very well. Now we can apply it on the Landsat images. Landsat monthly. Again, make a tuple and define an image collection. Call the time list, make a loop structure, define a function. Each date in the time list input for a monthly function. The function applies the monthly average on Landsat images based on existing date. So let's print the monthly Landsat. You can see 12 monthly Landsat returned. For each month, average NDVI and LSD calculated. Okay, now we have monthly Landsat and monthly evapotranspiration. we need to actually combine them into a single data set. So the final collection sets to get the Landsat monthly, combine it with ET monthly, just like this. Let's call the collection the ET monthly not defined. Month, it was monthly ET. Monthly ET. So again, we have 12 elements with 3 bands for every month. NDVI and LSD as a predictors and ET as an original variable. So the data set is now ready and we can calculate we can start the modeling or training the ET model based on. So now let's make another code and make another cell and convert the image collection format into the X-array structure. This step is very important. Thanks to the XEE library, now we can easily convert an image collection from the Earth engine into the Python environment using X-array structure. And after this conversion, we can apply the Python functions on satellite data easily without any challenge. So a new data set is going to create from an image collection from XR called the open data set. The input is the collection and engine is EE. CRS EPSG4326. Scale is based on a degree here. 1 degree is 100 kilometer roughly, 0.110 kilometer. I prefer, for example, 100 meter because for the modeling purpose, the 100 meter works well, and also it helping me to have a good speed of processing. Region of interest sets to the ROI. Let's run the data set. So the data set is created. If you print a data set, you can see the image collection format no longer available. Now we have a multi-dimensional array structure with 3 variables, NDVI, LSD, and also the evapotranspiration. Their data is available through the time, longitude, and latitude. Here we have a array-based structure. From now on, the data set available in the Python, and we can use the Python functions and algorithm on this data set easily without any challenge. Before going further, in the first step, we need to sort this data set based on time dimension. Again, ds sets to get the ds sorted by time and actually multiply to 1. Doing multiplication here doesn't make any sense, and also it doesn't change anything in the data set. But experimentally, I learned that doing this simple multiplication increases the speed of processing for this data set in the next step, because a new data set creating apart from the original data set that helping us to have a higher speed of processing in the next step. So it's not scientific thing, just a kind of the trick I'm gonna share with you. So the data set is now ready, and I'm gonna actually convert it into a data frame structure, because in the data frame format it is very easy to train a model applied on a data set. So the data frame sets to from a data frame, let's call the data set, convert it into a data frame. Remember to drop the no data values. Let's call the data frame. Now you can see all the pixels values available in a data frame format. Now it is very easy to make a prediction model based on this structure. So now to make a model, we need to define some samples as a predictor, some samples as for example, the original samples. So First of all, we need to call the actually test and train or train test split samples using Scholar. From Scholar model selection, let's import train test split function. So now in the df, let's define the predictors using X. The predictors are NDVI and LSD, NDVI and LSD, and Y or the original variable should be from data frame. And the original variable is the evapotranspiration. The evapotranspiration name is like that. So X and Y predictors and original variables selected. Now we need to actually split our data for the train and test analysis. So let's make a new variable with four actually parts. Train, X train, X test, Y train, Y test. Okay, call train test split function with X and input, X and Y as inputs, original and predictors variable, random states sets to 42, and we are allocating 20% of input for the test analysis. So some of the samples gonna be used for the training like X train and Y train. Some of them gonna be used for the testing the model X test and Y test. So now let's run. We have the test and train samples now. In the next step, we need to call a model, a machine learning model, to actually train it based on existing samples. Again, from sklearn.ensemble. From sklearn.ensemble, import random forest regressor. So let's run. Random forest regressor, what it is. So the random forest regressor is one of the nonlinear machine learning models, help us to handle the relationship between relationship between original variables and predictors. Before going further, let me go a few steps backward and showing you actually how much LSD and NDVI correlated with the evapotranspiration. We already calculated the NDVI and NDVI and LSD dataset, and here easily you can see their correlation in the Colab environment and on the Python language. For example, I'm gonna have NDVI ET relationship analysis by the correlation function. From XR, call the correlation function. From DS, get the NDVI and ET ensemble. ET dot ensemble math. So just like this over time dimension. So here the NDVI ET finally or relationship could be plotted like this. X-axis sets to the Y, X-axis sets to the longitude, Y-axis sets to the latitude. As you can see, the longitude and latitude is available in this data set. And robust sets to the true. Let's run. So as you can see, here we have an agricultural area that shows the association between the NDVI and evapotranspiration. In the most of the areas, the correlation is above 80%. That shows there is a strong relationship between the NDVI and evapotranspiration. So this product could be a good predictor for the NDVI, for the evapotranspiration analysis. We can do the same for the temperature and see how much the temperature and evapotranspiration are also correlated. When there is a strong relationship between the predictors and original variable, meaning that we can use them as a actually perfect predictors to estimate the evapotranspiration for the rest of the areas that's not its product available. So now another variable, temperature and ET, from XR calculate the correlation, this time LSD ET ensemble method over temporal dimension. So let's get the temporal ET, plot the correlation, X sets to the longitude and Y sets to the latitude. No need to call, just robust, increases the contrast, should be true. So as you can see here, the correlation of the temperature and evapotranspiration is above 75%. That is a good sign. So meaning that our predictors, LSD and NDVI, both of them showing a strong correlation with the original variable. So now we can rely on these predictors to predict the evapotranspiration for our study area. So now we are sure that actually we made sure that the NDVI and LSD are good predictors, and let's call the random forest to define the relationship between the predictors and the original variable. So the model sets to call the random forest regressor, and n estimators sets to 100, number of the estimators, and random states sets to 42. Okay, then the model is fit based on X train and Y train. Train data already splitted by the trained and test split function. Let's run the model, and now we are waiting until the model is trained. The amount of the time for the fitting process depends on the size of the dataset and number of the samples. Higher number of samples, bigger dataset takes longer time, but definitely for such area and such model, it takes less than 2 or 3 minutes. If you're faced with any challenge in this tutorial, feel free to find the code example on my YouTube channel below this video in the description box. You can easily actually check out different codes in my program with yours and then find the solutions. So now you can see after 3 minutes fitting process is done, and now I can actually assess the model relationship, the model accuracy using the test data. So now from sklearn.metrics import, for example, mean squared error, and R2 score, for example. So let's run, and now calculate the R2 score sets to get R2 score function, bring Y test, and before this, the Y should be predicted based on a model. The model predict the Y based on X test. So let's run. The Y is predicted based on X test, and now we can do the rest of the analysis. R2 score sets to, or R2 score function, Y test, and predicted Y. So let's run the R2, and as you can see, the value is 81. It's very good. 81% of estimated values are correlated, or actually explaining each other, meaning that there is a strong linear relationship between predicted values and original values. And also using the mean square error is another parameter that shows us how much estimated values actually far from the original values. So we know that the estimated or predicted value is highly correlated, but the absolute value could be a little bit actually far from each other. That makes sense. And also we can calculate it using mean squared error. So RMSE sets to mean squared error, y test, and y predicted. RMSE, let's run. But remember that to calculate the square root, so import numpy as np. Now np.sqrt should be added here. So finally it's about 23 millimeter, the absolute values differences from each other or far from each other. They are highly correlated, but the absolute values are a little bit far. How we can make it better, the absolute differences between original or predicted values? You can increase the number of the predictors, some things like the land cover or etc. And also we can even use a stronger model such as the deep learning model to actually get a better estimation for the RMSE event. But as long as the R square is around 81%, actually the values are reliable and highly correlated, and also 23 millimeter differences, it is not a very big value. And also now we can trust to this model for the next analysis, because I utilized this analysis and compared the results with the other existing products, and the final estimation is satisfying and the values are in expected range, and we can rely on for the extra analysis. So now the model is ready, and now we can call the Landsat images in this area, or we can calculate the evapotranspiration for this area and compare it with the original one to see how much they are different to each other. So the data frame already had the evapotranspiration, but we need to add the predicted value. So sets to from the model predicted evapotranspiration based on NDVI and LSD, just like this. After a few moments, a data frame including original and predicted evapotranspiration together, and then we can do a visual comparison to see how much results are actually correlated or how much they are similar to each other. You can see we have original ET and predicted evapotranspiration values, and then we can return it back into the X-array structure and we compare them in the visual format. In addition to quantitative assessment, we can have a visual assessment to see how much results are reliable. DFX, because we want to convert it into the X-array, get the df.2x array structure. Remember to sort it by longitude, latitude, and temporal dynamics. So sort by, so there was a typo here. So dfx now is ready. Let's make a plot from the original evapotranspiration. Select the original ET just like this, make a plot. X-axis sets to the longitude, y-axis sets to the longitude, y-axis sets to the latitude, robust sets to the true and call sets to the time. There you go. And also call wrap sets to 6 because we want to have 6 map per row. Let's run. This is original evapotranspiration for the region of for the study area. So as you can see, the ET is very low and increases as vegetation grows. The evapotranspiration also increases in this area. And ET ranges from 25 millimeter to 175 millimeter per month. So now we can do the same analysis. We can actually do the visualization for predicted ET. Just copy the value and paste it here. This time predicted ET. So now as you can see, visually they are really correlated and close to each other, and the range of the value also is very close to each other. Although actually you can see the RMSE is not very good, but the range of the values are really close to each other and estimations sounds good. So that means the model is reliable. Now I can extend the model for another region that OpenET product is not available. So I'm gonna select a new area and calculate or predict the evapotranspiration for that region that OpenET is not already available. Map number 2 from GEE map, call another map with a new base map with a satellite background. Let's call the map number 2. Here as you can see, the global world is available, and I can go to Iran in the southwest of Iran, agricultural area available here, and I'm selecting a small area to predict the evapotranspiration for this area that OpenET is not available based on the model. So now ROI number 2 sets to from map number 2 gets the last feature just like this, converted into a geometry. ROI number 2 is created. So what is the next? In the next step, I need to call the Landsat 8 and 9 because we need to have NDVI and LSD to predict the evapotranspiration. So hopefully Landsat 8 and 9 available for all around the world. We will have no problem here. Just copy and paste them into the new cell. Just like this. So Landsat 8 number 2, Landsat 9 number 2, because I want to keep them separate from the original Landsat 8 and 9. And for the same year, and ROI number 2 should be ROI number 2. ROI is number 2 again, but the time start and time end will be same. So now I'm gonna make a new collection, and even we can compare them to the monthly format, same as before. Landsat monthly. So Landsat number 2, Landsat 8 version 2, Landsat 9 version 2, Landsat monthly number 2, time list is same. Landsat here should be Landsat 2. Okay, let's make a print. Landsat monthly number 2. Let's run. And here again, 12 elements returned. And here you can see 2 bands NDVI and LSD available. So now we have NDVI and LSD in this region, but ET is not available, but we can predict it. Convert the Landsat monthly number 2 to the X-array format. DS number 2, X-array open dataset, Landsat monthly 2, engine sets to EE, CRS coordinate system EPSG4326, scale 0. The resolution here, I prefer to have 30 meter now, because for the modeling I utilized 100 meter. Now for the prediction I prefer higher resolution, because I need a higher accuracy and higher quality even. So the geometry will be ROI number 2. Let's run. Okay, DS number 2 created. We need to sort it. Sort by temporal dimension. Multiply 1 to increase the speed of processing. The DS number 2 should be converted into a data frame structure. DS2 into data frame structure. DF number 2. And here you can see the NDVI and LSD values available for every pixel. The model is already created. Just we can predict the evapotranspiration using the model. Model predict DF number 2 based on NDVI and LSD. So the model is already created. Just we are actually predicting the ET for a new area based on existing NDVI and LSD. DF number 2 is run, and you can see the new ET calculated. So we can return it back into the X-array format, DF2 to X-array format. Remember to sort it based on spatial temporal dimension, latitude, longitude, and time. Let's run. DFX number 2. Let's run again, and ET is available. Okay, select the ET and make a plot. X sets to longitude, Y sets to latitude, call sets to time, and call wrap sets to 6. Let's run. And remember to apply the robust to increase the contrast. So now, as you can see, for this area, open ET value calculated, and the evapotranspiration value ranges from 20 millimeter to 140 for this area. That makes sense. When the vegetation cover grows in this area, the amount of evapotranspiration also increases, and also that's really beneficial for us. Now we have the open ET for our study area, while it is not available previously. So now you saw that how actually we did a modeling structure, modeling purpose for this area. Even we can calculate the whole average ET for this area and make a graph easily and without any challenge. For example, here I can make a new code, and for example, the DS, this is ET average, for example, sets to get the DFX2 to or dot mean, get an average over latitude and longitude, over latitude and longitude, dot to the converted into a data frame, just like this. This is ET average, so something's wrong. Latitude and longitude. Now you can see the NDVI, LSD, and evapotranspiration is available, but we only need the ET. Let's run again, and this time you can see the evapotranspiration is available. You can make a plot, and here you can see how evapotranspiration varies in this area for 2024. And here even we can set a marker to mark the month variations as a point that shows how evapotranspiration dynamically change from one month to another time. So I hope you like this tutorial as much as I did. If you face with any challenge or problem in this tutorial, feel free to reach me out and put your comments, and please share this tutorial with all of the remote sensing fans in all around the world. Thank you for your attention.